Accelerated computing revolutionizes inference in high-dimensional experiments with enhanced rigor.
Is large-scale inference. So we've solved this compute bottleneck. We've solved this memory bottleneck, and now we can perform this rigorous design respecting inference conditional on acceptance. What this will allow us to do is generate a pool of accepted randomizations, and then from that we'll be able to select the randomization that we want to use in our experiment. We'll sample that uniformly, and then after we run the experiment and get results, we can perform randomization inference using that pool of acceptable randomizations that we obtained using this accelerated computing framework. And this will allow us to compute exact p-values and fiducial intervals, which will honor the theoretical foundations of experimental design while having none of the complexities of sequentially adjusted re-randomization protocols. What does this mean going forward? I think what this means is that the area of representation-rich high-dimensional experiments is really here with these innovations in accelerated computing. Now we can readily incorporate large high-dimensional covariates from deep neural networks, from visual embeddings, from satellite imagery, or from these text representations. And we won't need to, in the same way as previously, compromise on statistical rigor due to computational limits. Here, as we unify batch computation, hardware acceleration, among this sort of memory-efficient keys-only storage design, we'll be able to extend the gold standard of randomization design to the scale of modern high-dimensional data. Thank you for listening.